let's just get started. So I will give the first sort of tutorial of the day where you will actually be sitting here and coding along and having fun. So I will talk about reading NWB data from DANDI. And, you know, one of my mentors once told me a good talk has to start with a joke, and a good tutorial has to start with establishing the credibility of the instructor. So let me see if I can do this in one sentence. I am the PI of the NWB project, and as you all know, the best person to ask for low-level technical advice is always the PI. So for those of you who thought it's funny, we have a big team in the room of other people who are also very technical and can help you along, but I've also done coding along. And for those of you who really thought that was true, I'm glad you all had these great mentors that are both technical and scientifically advanced. So for this particular tutorial, so let me start off with, you all got some sticky notes handed out, okay? Those sticky notes are here so I can see when we're ready to move on to the next phase of the tutorial. So for this one, take down all your sticky notes from your laptops. Step one. Step two, go and download the notebook. And when you're done with the download and you all have access, have the notebook ready on your laptop, not running, just download it. You'll put the sticky note back on your laptop. And this way, none of you have to raise hands when it's for, I'm done and ready. But if you have questions, if you run into any issues, we have Ryan in the room, we have Ben in the room, we have other people that can also come to you and help you along. And then, I don't know, Ryan, if you also want to post the link in the Slack, if that's easier for folks. All right. So far, I only see 3 sticky notes, so people are still downloading. And if you're working on something else, then just leave the sticky note up, and I will just take it as I am ready either way. All right. All right. I see increasing numbers. I will give you 1 more minute, and then so in the meantime, while you're working on this, how many of you are planning to use your own laptop? Just raise your hand to run these notebooks. Okay? How many of you are planning to use the DANDI Hub to run stuff? Okay, we got a few. So we'll walk through both options. So if you're running locally in your Jupyter environment, please make sure that you install these packages that are listed here. So DANDI, pine.v, remfile, and matplotlib. Those are the packages that will be used by the Jupyter notebook. Okay. And then while our local folks are installing those packages, let me make sure we can also get everybody set up that is working on the DANDI Hub. All right, so if you're working on the DANDI Hub, and I'll just go through with you these steps one by one. So we will also need to make sure that you have an environment set up, okay? So the first thing I want you to do when you're on the DANDI Hub, you can go to File, and then, Services, and then there is Environment Management, okay? So that's where you can configure new environments. Now, if for some reason this shows that you're not logged in, you might have to hit the login button again. Okay? And then you just hit this little plus button to create a new environment here. And, you know, you just give it a name. Okay? And then the next thing you're going to do is you're going to pick this little configuration script here in YAML, and then you're going to switch over here in the specification over to YAML, and just going to copy that in here. So that will, you know, give you PyNWB, Matplotlib, a REM file, and DANDI, all the packages that we need to run the notebook in your environment, and then you're just going to hit create. And then it's going to spin for a little while for you here while it's building this environment. Okay. And so while it's building the environment, you can also then grab the notebook that you have downloaded and just drag and drop it into the sidebar, and that will upload the notebook so you can run it inside the DANDI Hub. So I will give you, a few minutes for this to finish. I know it takes a couple minutes to build the environment. And yeah, please just raise your hand if you run into any problems or issues.
Oh, yeah. It can take some time to start up.
Ryan?
Yep. Do you have the ability to download onto your where is it downloading? So it's going to download into the same folder as wherever your notebook is.
Yeah.
Question.
Yes.
The
Yeah.
data will be
So
downloaded to the
download
folder.
Okay,
Is it
okay.
small enough for our laptops, or should we get out like external?
It's small enough. I think it's like 80 megabytes, but I'm using here.
Okay.
Did not download it.
That's odd. So go back to the DANDI page that you were.
I try to not use
Go-
huge data sets for
go,
tutorials, just for convenience purposes.
Python now?
Go back to the Python notebook, yeah. All right. So if you do this manually, go to down DANDI sets 004, click
Yeah,
files.
that will work
Oh no, not that.
All right.
for the file.
Let's see how far people are.
It was a P11.
If you could take down your sticky notes again,
Download there. And
make this nice and active.
out of storage space.
Now, your next task is to open the notebook.
So you just have to make some space.
All right, so you just double click on it when you have uploaded it. In DANDI, it's going to ask you which kernel to use when you double click it. So you select the environment that you've built. Now, if that environment for some reason is not listed even after you've built it, just go here, you stop the server, restart it, and then usually it will pop up. And then the first thing I want you to do once you have opened the notebook, run this cell So running a notebook cell is just shift and enter with all the imports, okay? And when you have run that cell with the imports and it completed, then you put back your sticky note. Because once we're here, then we're ready to actually start the tutorial. All right. Some of you are very quick. Others are still, and in particular, folks that are using the DANDI Hub, I think will probably need a few more minutes just to get set up.
Uh-huh. Uh-huh. Okay. So go back to the GitHub main, the DANDI main page.
Which kernel to select?
What?
There's a kernel list, like in the
Because we have to register. Did you register?
in the document.
Yes. Yes. However, the DANDI team needs to approve your registration.
Yes. So
And
you did the setup of the kernel?
it's Sunday, so
The way we walked through it?
it might not happen today.
Okay. So
Yes.
let's just go here. To,
Yes, yeah, just for like, we're just doing tutorial stuff
Okay.
today, so
Sorry,
I hope that's going to be okay.
And you go into environment management.
Mine goes
Okay.
to the wrong.
Hit login.
Looks different.
And then let's
Go,
go back to.
okay, I think you're in just the environment manager, so just go to the URL
let's do this
hub.dandiarchive.org. So we're going to get out of this environment manager.
Now you can hit plus. Name it whatever you want. This is the environment you're using for this particular tutorial.
Okay, so you can drag and drop your notebook into there.
Go to the notebook real quick. Scroll down. And copy this text here.
This,
Yeah, just scroll up a little bit. This channel,
the whole thing.
yeah, just copy that. Go back to your Conda store. Go here,
No.
switch that to YAML, and just
Wow,
replace
okay.
all of that.
Another way is just to hit the upload button.
And you hit create. Now this is going to build the kernel for you. Okay.
Okay,
That is done.
double
spinning.
click the notebook,
The kernel is built, and then you can select.
and
that
then
kernel within
the kernel doesn't show up here, so you have to restart the
That's what this is
server thing. So hit the top left button,
To get to a consistency
there,
so everybody knows
hit
what
stop, and then start, and then double click the notebook when it opens and select your new NDRH 2026 notebook.
For those of you who are already done,
Launch.
you know, just be a little
And
bit
then
patient.
hit start.
It just, you know, we're trying to get everybody to a consistent state so everybody is actually able to use the data going forward. So the initial tutorials always take a little bit, a couple minutes extra just to make sure we're all on the same page. But I see more and more white tags coming up. So.
How's it going?
I remember, Ben, how long do I have for this?
Work in progress.
Okay.
An hour. So until
Okay.
when? 11? 11:30. Okay. Well, we didn't have many MATLAB people, so we might cut that part short. Because, I mean, once we're here set up, getting through the actual tutorial, we can pace that a little bit. But
How's it going?
We won't have as
Good.
many stops once we're set up here.
The environment to build.
Okay. All right.
Oh, by the way, so I also created an environment,
Uh-huh.
local environment.
Yep, local environment, that's
How
good.
many people are still waiting for the environment to work?
How should I install Jupyter Hub and Lab and?
You just need Jupyter to run it locally.
All right.
That's, well, you need to install it. So,
Only one of those.
so pip install
Yeah.
Jupyter.
All right. We'll start moving on then.
Then use the Jupyter.
While Ryan
lab
is finishing up the last few pieces. So at this point, you should have all been able to run this cell where we're importing our basic libraries, right? So there's, on the one hand, we're importing, standard Python libraries.
Locally is
We're importing the DANDI client. So the DANDI client is used to retrieve data from DANDI, to download data, to figure out what are the URLs for different data sets, and so on. And then we have NWB, which we're using here to read the actual data in Python. Right? And so the first thing we're going to do is we can download the data from DANDI. We can do this in a couple of ways. So Ryan already showed this. You can go to the DANDI archive itself. We're, in this case, using DANDI set number 4, right? And then you would go to the files link. In this case, you go to the second folder, and then you would download that file. I'll make it easier for you. We can just download the data through the CLI directly. So you just go through, and then here in this third cell, you see we're specifying we want DANDI set number 4. We want this particular file from that DANDI set. We're creating a DANDI API client. We're telling it the DANDI set and the asset we want, and we call the download function, and that in turn goes ahead and downloads the file. In my particular case, I had already downloaded earlier, so it's a no operation in this case, but it's 72 megabytes, so it should go fairly quickly, whether you do it locally or on the DANDI hub, to get that file. Yeah?
A couple questions. One is, where does it download it to by default? Is it just the current directory?
Yeah, this currently downloads by default to the current directory, I believe.
The DANDI CLI, like it just recognized the actual it's working as a Python package, but it's not working as a CLI.
I can check.
Okay. Yeah?
So if I'm looking at something,
Yeah, we're trying to figure out how to just manually add it to my path. But I don't know which part of it is.
We'll do this when we do streaming. So you can, like, for when you download the file, you just, in the DANDI web UI, when you get the download link, you can use that URL. But then also the DANDI CLI client, and we see that when we do streaming, you can get the S3 URL from the client directly. All right. Oh, sorry.
Are there different use cases for when you might want to use the CLI versus the app to download the data? Or are they both basically do the same thing?
So you're using UV.
They basically do the same thing, right? I mean, I think anything you can do in the CLI, you can do in the API. It's just a matter of what's more convenient for you programmatically,
Because you're a virtual
right?
I've never used UV before. I'm like,
When you're trying to put together a workflow, it's sometimes easier to be in the CLI, or if you're not a programmer, users they like to prefer the command line interface. But if you're working in your Python program, it's perfectly fine to just use the client that way.
So no speed difference, it's just
No, I mean, it's the same code at the end of the day. The CLI just builds on top of the API and just wraps that up. Okay.
Maybe everyone take their Post-its off and say if you're done downloading.
Yeah. Let's do that again. Sticky notes off, put them back on. If have downloaded it, have access to the file. There you go. I like your confidence. You have 2 sticky notes now, so you're very good. No, you're fine. I'll accept it.
That's the second command on the download function. Right now it's dot. And so,
All right. So there's still a few people working.
But you can send it anywhere you want. You okay?
yes.
Yeah. Post it if you have downloaded the data.
It doesn't matter. We will.
So I'm
It's just a matter of preference, really, where you want to run this right now.
where everything is downloaded. So I'm wondering how do I make this environment open at that directory?
So from the command line, you mean? Or from...
From terminal or
Okay, yeah, open terminal.
I think we have
the
a few more
environment has
people
been
in the
loaded.
back, and then
but it's on a C drive.
we'll give it one more minute, and I think then we
okay.
can
So
really
then,
hit the ground running
Do you know how to
and
navigate?
actually
the
dive into this data.
on
Well, it should. There's some specific command I'm forgetting. I can look it up. Don't worry. About
yeah, I forget how to do that.
Yes, don't worry.
Okay,
It's fine.
okay,
I have been going through the DANDI Archive there. So
Okay.
everything.
okay, great.
Sorry, conceptual question.
Yes.
So, for example, if I only want a subset of the data, for example, only the sorted spikes and not the raw data, is there a way to only download a portion of the data and not the?
So it depends on the file. So some data sets have split raw data and process data into different files, and then you just download the processed file.
Okay.
Most data sets have done that. But if you only want to download the processed part of a file, you can do streaming.
Looks like we're good to go. If
Cover at the
if
end.
we're not, then raise your hand and say
You can just
stop.
stream just the selected parts of your data set instead of downloading the whole thing.
So we can actually directly access DANDI from like a local.
Yeah.
Without downloading.
Yes.
Okay.
Yes.
Okay.
Streaming can be slower
Well, it depends
because it
on
doesn't
when the user
because the file's not local,
Right.
and
So,
the
Ben,
same kind of caching isn't
You're the expert.
clean.
The question
but,
is different versions of a file on
it's-
DANDI. Draft,
work.
published, all the
Yeah.
different versions. So maybe I thought that's a better question for you.
Yeah, so
Yep.
there are versions of Dandy sets. So you can publish a Dandy set, and then you can publish more versions, just like in additions to the book. Sometimes those versions, often those
Okay,
versions.
it's not a ZAR file, so
data,
unable to read.
data, but they could.
No module. Interesting. You don't.
trying to read it as a ZAR file.
So that shouldn't happen.
All right. So, in the interest of time and not delaying the schedule too much, let's get started with actually reading some data here. So the first thing we're going to do is we're going to use, and let me see, I should probably make this a little bit bigger for you guys, shouldn't I? So we're going to use this little method from PyNWB that's called read NWB. It's a little convenience function that does under the hood all the magic for us to open the file, figure out from the file path whether it's a remote file, local file, which backend to use, all these sort of things, and opens the file for us and then returns us the file object. And then once we have our NWB file, we can simply print it in a Jupyter notebook. And so what this does under the hood, it gives us an HTML representation of the contents of the file. So here you can see I have my session start times listed. I have different metadata that sits at the top level. There's our acquisition group. There's our stimulus group, which then has the different presentations of the stimuli listed. So you can click through in this representation to figure out what data is actually in the file. Right? So it's just a convenient way for you to explore and sort of see what objects are available in a little bit more visual way. Okay, and like I said, under the hood, the read NWB function, typically will in this case use the NWB HDF5 IO class to open that file and read it on disk. As Ryan already mentioned, NWB also supports ZAR as an alternate storage backend. So there's another class that's called NWB ZAR IO. And so if it were a ZAR file, read NWB would actually use NWB ZAR IO to open that file for you. But currently, I think the vast majority of data on DANDI is going to be HDF5 data for you. So that's mostly what you're going to do. And so now that you got that NWB file, if you actually want to figure out what IO object was used, you can just call the read IO property on the NWB file, which stores the I/O object that was used to open that file, so you also have direct access always to the I/O object that way. So that is typically the quickest and easiest way for you to open a file, is just to use the read I/O convenience function. Okay, so that's step one. Now we're going to show you a little bit more under the hood. How do I actually use the I/O myself? Right, that is what you would do if you need to do some more customization on how you want to open and read the file, as well as when you actually convert and write data, you're going to use those I/O objects. So let's use them right now. So I'm just going to close this file for now, and we're going to start over and open it now directly. So all we're going to do is we're creating this NWB HDF5 I/O object here with the file path. We're opening it in read mode. And then all we have to do is call io.read, and that again will give us the NWB file. Right? So this puts us back in the same state as we were up here. We now have an NWB file class object. That is identical to what we had above. Okay? Another common way that folks will sometimes use the I/O in their code is through these context managers that you have in Python. So where you say with this particular object as a particular name, so with NWB HDF5 I/O as in this case IO.2, and then within that context you then call NWB file IO.read and get your data back. What the context does, it manages now this I/O object for you. So once this context is done, this object gets automatically closed and destroyed, so you don't have to take care of yourself of closing the I/O. Now what that means for you though is I can only use this NWB file that I was reading from within this context, right? So I'm able to read this file, but now if after the context I'm trying to say, hey, I want to get my read I/O. Is this read I/O actually open? Now it will actually tell me, no, this read I/O is closed. And then if I want to print this NWB file, right, we also see now this warning here. Hey, the back end of this file has actually been closed. You can't read from this anymore, right? So that's just something to be aware of if you like using Python contexts. Right, that is a consequence of that. It manages that I/O object for you, but also beware that you're not using objects that you created within that context outside of it. Okay. So, quick raise of hands. How is everybody doing? Are we good? All right, very good. So now we're actually diving into our NWB file itself, right? And so I'm going to try to also introduce a couple of the concepts that you will need to know and keep in mind as you're exploring your data. And so the first thing we're going to do is we're going to access some simple attributes. So your NWB file object is really your entry point into everything inside of the file. And so the first thing we have here is these two times. There's a session start time and a timestamp reference time, right? So these are two different date times. The session start time tells you when did the session that this NWB file represents start, right? And then the timestamp's reference time tells you what timestamp are all the other times that are in the NWB file aligned to, okay? In most cases, you will see that your session start time and timestamp reference time are the same times, okay? That's usually how users like to use NWB files, that all their timestamps are relative to their session's time. But there are also labs that prefer that all timestamps across all their different files from all the experiments are already aligned with each other. And so they will then use a timestamps reference time that is different, such as a UTC time, where you use like, January 1st, 1970 as your reference time to where everything is relative to. And so then timestamps within an NWB file are always floating point offsets in seconds relative to that timestamp reference time. Right? So within an NWB file, all your times are assumed to be aligned to that time. So if I have an optical physiology recording and an electrical recording, all their timestamps are relative to that time. That is sort of a first structure that NWB enforces for the contents that are within the file. Because ultimately, time alignment is something that really only the person that acquires the data really knows how to do. Because there's always different methods of how you synchronize your signals, and that really is something that the person that acquires the data needs to do. And so that's a first concept you need to understand. Everything is aligned to a global time, and the times that you see in the file are floating point offsets in seconds to this time. So if you want to figure out the absolute time, take that at that floating point offset in seconds, and you will get the absolute time. Yes?
Do you incentivize people that use longitudinal recordings to split, for example, like a big recording into different days, like out to have smaller time relative to each of them, or?
That really depends on practice, on what the experiment is, what the sort of recording devices are, right? If you do a high-resolution neuropixels recording where you generate terabytes of data in a day, you typically will start splitting up because you don't want to generate a petabyte HDF5 file, right? Because most people can't handle such files on their compute systems. But it really, we don't really enforce how people exactly split up these kind of recordings. That really depends on how their pipelines work and how they're set up. But typically, we would say, hey, if your data gets larger than your 50, 100 gigabytes, you might want to consider splitting them up just for a utility kind of purpose, right? Because it becomes very hard to move that data then around as well. Yeah. Okay, so now that we understand time, we can look at basic metadata. Like Ryan said, we also have metadata about our subject. So we just call, sorry that I'm solo, there's NWB file.subject, and again, all these objects have their own HTML representations. You can print it out. So you see here we had a subject that was 16 years of age. It was a male subject. It was a human, and it had that human had that particular subject ID. As a sort of side note, a new NWB 2.1, which was just released 2 weeks ago now, or a week, there's now also HERD available as a new data structure inside NWB. What that allows you to do is to also link fields in an NWB file to external identifiers. So, for example, you have here subject species, right? NWB only requires that this is a free-form text field. You may specify this whichever way you like. A user may say mouse, a user may say mus musculus. And so by providing the linkages, for example, to the NCBI taxonomy, you can now say, I said human, but here's the identifier in the taxonomy that clearly defines and identifies the species I intended and meant, right? And the advantage of using ontologies and formal terminologies to describe the metadata is that when you go across multiple different DANDI sets and files, you can now say, oh, even though this person said mouse, the other one said mus musculus, I have the identifier, they both say the same thing, I'm confident it's actually the same species. So you will not yet encounter many files using this, but this is one of the things that is coming up. And I wanted to mention it also because if you're doing studies across multiple files, you might want to use it to sort of annotate the data for yourself, to do that harmonization of data as necessary. So I just wanted to mention it as one of the upcoming things. Okay. So now let's move on to accessing some actual data. So in this case, we have electrophysiology recording under a visual stimulus. So we're first looking at the stimulus. The stimulus on NWB file is a dictionary that gives us all the different stimuli that are present. In this particular case, if we take a look at this dictionary, there's only one particular stimulus presentation here. And we can simply load that stimulus presentation by accessing it with the standard Python dictionary syntax, NWB file.stimulus, and then we give it the name of the stimulus that we want. And that gives us the stimulus presentation. Once we have access to the data object, all data load is performed lazily in PyNWB, as well as in MathNWB. What lazy data load means is you're loading the data into memory when you request it, right? So right now, none of the bulk array data has actually been loaded into memory in your laptop. All we have done is we have extracted the structure of the file. We know where things are, but we have not actually loaded the data yet, right? So even when I go stimulus presentation.data, which is the actual data array, what I'm actually getting back is now an HDF5 data set. It tells me it has a shape of 200 by 400 by 300 by 3, right? And it tells me its data type. Still, it has not loaded any data yet. It just told you, here, I know now where this array sits in the file. This is its properties, but we have not loaded the data yet. To load the data, you use standard NumPy slicing syntax. So all we do to load the data is we say, stimulus presentation.data, and then in brackets, colon, we'll load the entire data in. If you just want one time step, then you would say 1, colon, right? Right? So this will now load it. At this point is where we actually loaded this array into memory, right? And so lazy data loading is what allows you to work with very large data sets, even on your laptop, because typically if you do a visualization like what you saw earlier when Ryan showed NeuroSift, right? When I do a visualization of a range in time, I really only need that range in time to show you. And that's what allows NeuroSift to stream data and show it to you in the browser, because it doesn't actually have to download a 50 gigabyte file. It only has to slice out that particular portion that it actually needs. Right? And so if you're working on a laptop and you're saying, oh, I have a 50 gigabyte file and I can't process it all at once, then you can actually stage it out and sort of chunk it up and say, okay, I'm processing it 1,000 time step at a time or something like that, and then still do that processing that way. Okay. So a quick note, right, on how time series work in NWB. So NWB has, like a lot of data that we do, electrical recordings, optical recordings, all of those are series over time. And so NWB has a core data type that's called time series, that all of these other types, like an electrical series for an electrical recording, optical series for optical recording, will inherit from. So they all have a common structure. One particular key piece of that common structure is the first dimension of your array is always time. So in this particular case, our data set, this is our optical stimulus, right? Has a shape of 200 by 400 by 300 by 3. What does this mean? 200 means we have 200 time steps. So there's 200 images that were presented in some form. The images itself had an X and a Y resolution of 400 by 300. And then 3, there were 3 color components, red, green, blue. Okay? So that's what the components of this array in this particular case are. If we were to go to an electrical recording, we would see a 2D shape, right? It would add number of time steps times number of channels. Okay. And then we can slice data out of this data set in the same way. So let's say we want index number the 31st image. We can simply, say now stimulus presentation.data. We'll give it the index of the time step that we want. And then we load the entire image and call, matplotlib.show. And in this case, it's an image of a race car that was presented to the subject. Okay?
So is there a specific reason why it's stored as EGR instead of RGB? Is that how would I do that?
It's a quirk of this data set.
It's an error in the conversion of the data. Well, so NWB requires it to be RGB, right? And then the user, on conversion, there was a mistake that was made in this particular data set where they swap the dimension, right? There are certain errors that are hard to check for because they're all values in the same range. So unless you actually start looking at the image and you will see, this looks inverted.
I have a question. If you need to correct this error when you upload the data, you need to request they take out the data and put it again? On upload, DANDI CLI will run the NWB inspector. NWB inspector has a large number of different checks in it. To do basic checks for both that the file itself is valid for NWB itself as a structure, but also that there are no quirky data errors. Certain errors are easier to check for than others. But, then the DANDI will already tell you on upload, hey, here is a problem. Some are considered critical that will prevent you from upload that you have to correct prior to upload. Others might be warnings that say, you should really include this information for it to be useful for others. I don't know, Ben, how many checks are there by now? Like 50 or so, I think? Yeah. And so also that set of checks is evolving, right? Where it's like, hey, this is a common mistake that we see people make. Then will become an error check in the NWB inspector that will be automatically run on DANDI upload. This data set that I'm using here is also fairly, one of the first data sets that came online. I just chose it because it's pretty simple, pretty small.
So could I fix these and push it up or something? Is there an optional editing that, if it's a common mistake?
No, I think the best thing to do would be to contribute a notebook that just shows how to read it, fix the errors, but you don't have you could publish a new data set with a corrected version of this, but then it gets messy, like attributing attribution to source data, so I wouldn't really recommend that. I would say contact the authors and contribute a notebook that demonstrates how to fix it.
Yeah. Okay. So now you've seen basic time series data. The next thing we're going to look at is single unit data. So this is after spike sorting was applied to your electrical recordings. You've extracted, these are the putative, recording units that you saw, the neurons that you observed, and that is stored in NWB file in the units table that sits at the top. So this is a table-based data structure, right? So this is another. Okay, I realize I'm running long, Ben. I'll steal a little bit of your time. So tables are another core structure that you find in NWB. They're used throughout, typically to store different types of metadata, such as information about electrodes and so on.
one advantage that tables have, they can also include custom columns. So without actually having to write an extension, you can add additional columns to a table to include more metadata. And so in this case, we have our units table, right? It has these different columns. If we want to look at a table, we do have the 2 data frame methods available in PyNWB. So they will load all of the data in to memory off that table and then convert it to a pandas data frame for you. So you have it available conveniently in your standard pandas method. So here we're just looking at the first 4 units, right? So we have our cluster ID, we have our waveform means, and then we also have, the times when this unit was spiking and so on. And so to access the spike times itself, we have the spike times column. So all we do is we can go into this data frame, or you don't even need to convert to the data frame. You can just go to NWB file.spikes, .units, and then you slice into it with that column name. And in this case, we're just extracting the spike times of our first unit, right? So this now loaded all these spike times into memory. So as an example exercise here, what we're going to do is we're going to take the first 3 units of our table, and then we're going to align all of the spike times to the onset of our stimulus presentation. So we're taking all our stimulus presentations, what happened at different times, and we have our spike times. And so we're shifting them relative to that, and so that we get an overview for each unit of when does it spike relative to the stimulus presentation onset. So in this code, we're iterating our first 3 units. We're loading that particular unit's spike times, and then for each of the spike times, we align it to our stimulus time, and then we're going to plot it both as a raster plot and as a histogram. So what the raster plot shows you here is you have the dashed line, which shows you when the stimulus was presented, and then you have the dots giving you for each particular trial when the unit was spiking. And then the histogram just shows you the distribution, the probability of how likely is this neuron to spike before and after the particular stimulus presentation. Okay. Now the next major sort of concept that you will find is, in addition to, here's my raw time series data, here's my sort of processed results, are then also the organization of the actual experiment into a trial structure. And so NWB, again, uses data tables to organize data into time intervals. There's a top-level intervals folder for that. And then there's a dedicated trials folder. And so, again, we can just say NWB file.trials. We'll convert it to a data frame. And so for each trial, we will have a start time, a stop time, and then different sets of columns. In this case, there's also a large number of custom columns that the user added, such as what is the category of stimulus, what was the name of the stimulus, and so on. So you will find additional metadata in those columns. And if we don't know what this column means, there's typically going to be then a custom description also associated with that column. So in this case, we have stimulus phase. I don't know what that means. And then the description tells us it's going to be learning, that it is a learning recognition phase during the trial. Again, just as a side note, in the recent release of NWB 2.10, we also added now this concept called a meanings table. And what a meanings table allows users to do is to associate metadata with the values of a column. So in this case, for example, we have this category name column, right, where it says landscape, mobility, right? I don't necessarily know what these terms mean. So with a meanings table, I can now say, I want to associate meaning with this category name column, and then provide additional metadata for each of these terms that is there to describe what they mean. In this particular case, this is an older file, so it's not going to have any meanings tables yet associated with it, and I doubt you will encounter any meanings tables at this point, but it's a concept to be aware of that will become more and more prevalent, as well as if you're using data if you're trying to annotate data with additional information, this can be a very useful tool to do that. Okay. So now let's take a look at visualizing some of the stimulus images by a trial. So in this particular case, we have each stimulus has an onset time when it was presented, and we know the trial starts with that presentation, so all of those are the same. And so what we're going to do is we're going to visualize the first three images that were categorized as a landscape in the particular session. So all we're going to do right now is we're going to go to the trials data frame, we're going to look at the category name, we're going to pull out landscape as the key, and then we're going to plot those images. And so these are the first three landscape that were presented to the human subject in this particular case. Okay. And as Ryan mentioned, there's lots of other additional tools like NeuroSift that you can also use to sort of explore data online. I'm going to spend now 5 minutes also showing you streaming, and then we're going to move on to Ben. I know I've cut into your time, Ben, now. Apologize for that. But I will say Ryan stole a few minutes from me already, too. All right, so when we want to stream data, it looks, what streaming means is you don't want to actually download the whole data. You just want to be able to take a look at the file and get pieces of it, right? And that's, again, where lazy data loading comes in, is I want to be able to look at what's the contents of the file. I want to be able to get a few bits and pieces, like I want to get 1,000 time steps just to see how this particular data looks like what you saw in NeuroSift. I just want to create this plot. I don't need this whole 50 gigabyte file for it. I just need a couple of megabytes from it, right? And that's when streaming is very useful as a tool, because you can leave the data in the cloud or wherever it is stored remotely and just access it that way. So there's dedicated tutorials in PyNWB how to do that with various different methods. In this particular case, we're going to use REMFile to do that. So the first thing we're going to do is we're going to use the DANDI client to get the S3 URL for that particular file that we want to access. So again, we specify the DANDI set ID and the name of that file within the DANDI set. Then we're going to call client to get the DANDI set and get the path of that asset. And then we're going to get the content URL, which is our S3 URL. Right? And so in this particular case, that's going to be, DANDI Archive.s3 Amazon AWS.com with that particular number. And so once we have this URL, we can plug that in directly into our library. So you just call REMFile. You create a REM file with that S3 URL, and then you can take that REM file, plug it into an H5Py file, and hand it over directly to NWB HDF5IO. So really, the only difference between you reading remote and reading locally are these two lines. Right? You create your REM file, create the H5Py file. Now at this point, you have access to this remote file. You just tell it to NWB HDF5IO, and you just call read, like you do normally. So at this point, this NWB file stream looks to you exactly the same way as if you had it locally on disk. Right? The main difference is you might see some performance difference because obviously a local disk is going to be faster than accessing remote. But for most basic operations, that's fine. So I can again, just look at my file structure, and I see everything that's in the file is the same as we saw earlier. We can again go ahead and load our image out of that data set. And again, now at this point, this image was actually streamed in interactively into the laptop and then visualized here. Or in this case, I'm running inside the DANDI hub, so it was accessed on S3 through the DANDI hub. And then at the end, always good housekeeping, close your IOs. It's just the right thing to do. And with that, I am 15 minutes over, so I will hand it over to Ben, and I'm open for questions. All right. So you have now officially survived